Hello and welcome to the Stephen Academy online review of AP Chemistry. Today we will be discussing the basic overview of the test as well as some of the specific changes that have happened to the curriculum in the latest update. The AP Chemistry test, first of all, is one of the rarer tests that shows up on college admission. Roughly 100,000 students take it per year. And it has some distinction among the other APs for being a test which typically, of all the students which take the class of AP Chemistry, only about half of them end up actually taking the test at all. So it's common to see it on curricula, on people's CVs and transcripts, but less common to see it as an actual test score. So even getting a 3 on this exam is still indicative of additional effort on your part. By and large, the test is scored as all the APs are on a 1 through 5 scale. However, there are a couple of changes that were made to the test most recently. First of all, the test is now slightly longer in the free response portion, and there has been a decreased focus on multiple choice questions as well. So let's break down the test, just so you know what to expect from it. It's a 3-hour and 15-minute long examination, which is taken in person. The format is a section 1, which is composed of multiple choice questions, or MCQs, for which you will have 90 minutes allotted. During the multiple choice questions, you will not be able to use a calculator. However, you will be provided with a periodic table as well as several pages, well, 1 or 2 pages anyway, of relevant formula, which you will be able to refer to during these questions. There are only 60 multiple choice questions, meaning that you'll have about 1.5 minutes for each multiple choice question. There are also only 4 choices per question for you to choose from. In past years, it was 5. So this is an improvement because now you have less things to consider. There is also no penalty for guessing, whereas previously if you got a wrong answer, points would be deducted from your score. At this point, the way they think about it is if you get the question right, then you get the points. If you get the question wrong or you don't give a guess, that's considered the same. So you absolutely should guess on any multiple choice question, even if you're unsure. If you can eliminate 1 or 2 or 3, well, if you can eliminate 3 questions, then question choices, in that case, then you know the 4th one is the response. But even if you can just eliminate 1, that still gives you a great reason to guess. Even if you can't choose 1, you still have a 25% chance of getting a point. So guess, by all means. Don't waste time and don't find yourself running out of time at the end of the test to the point where you have questions that you have not answered. If that does happen and the proctor says, there's 60 minutes remaining, 60 seconds left, you're about to put your pencils down, go ahead and fill in something for all of the answers, even the blank ones that you haven't come up with an answer for yet, okay? Don't leave anything blank on the multiple choice questions. That's the main thing I would say. Okay, after the multiple choice question section, you will then have the essay section, which is longer than the multiple choice question. As I said, this is where 15 minutes was added to it. You will be asked 3 long-form questions, which may typically involve data from a laboratory experiment of some kind. And then you will have 4 short answer questions to answer, which will typically be looking at a more specific aspect, either of a laboratory experiment or of a situation or scenario or some type of concept, such as those that we'll be talking about in this exam. Okay, so one other thing about the essay question is that they are allowed to use calculators on that. In addition to having access to the periodic table and the relevant formulas, you will also be given access to a calculator. You should bring your own. The College Board has a list of calculators which are approved for use on this. Don't just bring like a little 4-function calculator that can just do basic stuff. Bring something that has a graphing capability, or they can handle logs and exponents and stuff like that, because you want to be able to do all of the formulas that are on the test, right? And some of those are a little tricky. Okay, Now, let's take a look at some of the specific changes to the curriculum that have been made since our last video series on the subject. Let us now consider some of the specific updates to the AP Chemistry curriculum that have been made recently. In my experience, recent updates to the curriculum are often a good source of questions because they want to make sure that everyone is paying attention. So it behooves us to consider them in particular. First of all, there are some changes that were made to the language describing how alloys function. Recall that alloys can be substitutional or interstitial and occur when two or more metals are combined such that their atoms are placed in a close proximity to each other, right? So instead of being a bunch of copper atoms that are all together and a bunch of zinc atoms that are all together, they're actually mixed together. And typically this occurs at high heat. You melt the two metals, they mix together, and then you have a new alloy at the end of that. The thing with alloys is that they are very important in human history because the ability to produce an alloy often gave you massive advantages over either of the two metals that you start with, okay? And the best example of this is bronze. Bronze is formed from a combination of copper and tin, which are both in themselves very soft metals, and they're very pretty. You can use them to make pipe out of, but they're not very good for making hard implements. But if you melt them together, melt the copper, add a little bit of tin, you get bronze, which is a much harder substance and can be used then to make knife blades, axe blades, things like that, things that are actually usable, and edges that will hold, for example, so that you won't have to be constantly sharpening them. So this particular property of alloys, where if you have something that ends up harder than the two things that you started with, seems to be particularly stressed in this curricular update. Alloys of metal lose ductility and malleability, which is what it means when we say that something gets harder, is that if something is soft, then you hit it with a hammer and it takes the new shape that you've been beating it into, which is what malleability means. That's from malleus, which is the Greek for hammer, means you can hammer it. And ductility means that you can pull it into a wire, which is another, if you think about it, like hammering is like pushing and ductility is pulling, then much like if you're using something that's very soft and squidgy like bread dough, that has very much malleability as well as a lot of ductility as well, okay? So when you make an alloy, it's going to end up having less ductility and malleability than the two metals that it began with. However, it will retain conductivity, okay? And that's because when you have a metallic solid, even if it's different atoms, they will still all be sharing electrons between the nuclei. You'll still have this sort of like sea of electrons, which are, because they're all metal nuclei, they can pass electrons back and forth in this way. And it doesn't matter that they're not all copper or that they're not all tin or whatever. They can still pass the atoms back and forth. And that isn't impeded by making an alloy, okay? So this is just as true for substitutional alloys, like bronze, where you're substituting some of the copper atoms with tin, or with interstitial alloys like stainless steel, where you have a lattice of iron and then inside the lattice you put carbon, okay, sort of to fill in the crevices, okay? Both of those cases you end up with something that's a lot less malleable, less ductile, but still conductive, both to heat as well as electricity. That doesn't change, okay? All right. Now, another thing that they changed some of the language related to was the question of covalent network solids. Think of these as what happens with any crystalline substance, such as, for example, salt. Okay, salt has a crystalline macrostructure, which is indicative of the bonds between atoms at the micro level, okay? So basically, what this language wants you to consider is that the covalent bond geometry of a bunch of molecules, right, that all have the same arrangement between atoms within them. If you take a bunch of those together and form a networked solid, which is when you have all of these similarly shaped covalent molecules that are stacked, basically. The way that they stack depends on the 2D or 3D structure of covalent bonds in the molecules themselves, okay? And so if you can have substances that have similar empirical formulas, the same number of different atoms in each molecule, but if their geometry is different, the way that the bonds form is different, the structures at the large and visible scale, the crystals that will grow, for example, will be of different shapes and different configurations because it's based on how do the covalent bonds form between the atoms, okay? Now, speaking of molecule stacking, another change to the curriculum was surrounding the question of hydrogen bonding. Okay, and this relates to the overall question of dipole forces and intermolecular forces, okay, which is a broad category, what was formerly called van der Waals forces. And it's basically interactions between molecules that don't rise to the full level of a bond. Like it's not as strong as an ionic bond, where there's a one full negative electron charge that is holding at least that much, that is holding two atoms together using electromagnetic attraction, okay? Or a covalent bond where they're actually sharing an electron, they're held much more tightly, okay? Below those levels, there are these dipole interactions where a dipole is basically anything where you have, within an object, you have a negative part and a positive part, which might be thought of then as poles. You have a negative pole and a positive pole. And because we're talking about negative and positive charges, that means electrons, because you can't move protons around inside of a molecule, but you can move electrons around. And so anytime you have a situation where the electrons in a molecule are tending to spend more time over at one end of the molecule, that end of the molecule will tend to have a more negative charge, and the other end of the molecule will tend to have a more positive charge, okay? Now, the reason why electrons would tend to spend a little more time over at one part of the molecule as compared to another has to do with the question of electronegativity, okay? Which might be thought of as a given atom's nucleus's affinity for electrons, how much it wants to have an electron around. Before we get too anthropomorphic here and try to ascribe desire to subatomic concepts, remember that when we're talking about electronegativity, we're talking about a thermodynamically desirable situation where there is less stress on the system and the orbital shells are filled harmoniously, okay? So it's not that these atoms want to have electrons around them. It's that they are more stable when they have the full complement of electrons around, and therefore electrons that are around them tend to be there. They tend to hang out over there because they're filling out a role that is more thermodynamically equilibrium, okay? Now, the specific change that was made here when we're talking about hydrogen bonding, which is a form of dipole interaction, which is a type of intermolecular force, is that they want you to pay specific attention to this electronegative atom concept, okay? So anytime you have hydrogen bonding, it's easy. They recognize that you get distracted because you're just thinking about the hydrogens, okay? And the thing about hydrogens is that they don't really have very much electronegativity. They don't really hang on to their electrons very much. In fact, a good number of hydrogen atoms are just the proton, just bumbling around on its own with a positive charge, okay? so it doesn't really have a high degree of electronegativity. And if it ends up in a covalent bond with an atom that does have a great deal of electronegativity, this forms a strong dipole between the hydrogen, which is not so electronegative, and the atom that it's bound to that is very electronegative. The electron tends to spend more time with the electronegative one, tends to have more of a negative charge over on this side, and the hydrogen atom tends to have a more positive charge, okay? So the three that they want you to remember are nitrogen, oxygen, and fluorine, specifically as the most electronegative. And what that means is that when you see an equation where they're asking you what is happening in this reaction, why is there something going on here, and there is a presence of a hydrogen bound to a nitrogen, an oxygen, or a fluorine or something, be suspicious that that's what they're asking you to think about, is hydrogen bonding. So the way this works, right, you've got hydrogen bound to a fluorine, right? Because the fluorine is more electronegative, the electrons are going to spend more of their time over down on the fluorine side. So that's going to tend to be a little more negative, and the hydrogen is going to be a little more positive. When you have a bunch of them in a solution that are all together, or that they're all able to move around in relation to each other, then the hydrogens of one will tend to be attracted to the electronegative atoms of another molecule, okay? And this sort of leads back to the whole question of how covalent network solids get their structures based on the covalent bond geometry. Because you can have more than one hydrogen coming off of some of these, you can end up with dipole, more than one dipole within a molecule. This is best seen, for example, with a water molecule, where you've got two hydrogen bonds coming off of a central oxygen, right? Which means that the central oxygen tends to be the more electronegative, and then it has these two positive charges. So it has two things that it can be attached to other oxygen atoms, and like that on down the line, okay? Now, what they want you to recognize in hydrogen bonding is that it's the hydrogens of one molecule being attracted to the electronegative ions of the other molecule, okay? If you don't have nitrogen, oxygen, or fluorine in the mix, then you're not going to have as strong of a dipole created between the hydrogen and its central atom that it's bound to, okay? And therefore you won't have as strong of a dipole, you won't have as strong of an interaction between neighboring atoms that are relying on their dipole to cause them to be associated, okay? But hydrogen bonding in and of itself, when it is working this way, is pretty strong. It's just about under an ionic bond, but it's still pretty strong, especially compared to some of the other forces that you have to talk about, like London dispersion forces, which are really just reliant on all of the electrons happening to be over on one side of the molecule, creating an instantaneous dipole, which soon dissipates because the electrons then happen to be over on the other side. You know, they happen to move around. When there isn't like an electronegative force is drawing them over to one side or the other, they just happen to be on one side or the other. That creates a tiny little dipole that, whoop, and then as soon as it disperses, then so does the attraction between neighboring atoms. Okay, we'll talk more about that in the high yield portion. Believe me. All right, moving on. The next thing we will consider for the AP Chemistry curricular update are some of the language pertaining to electrical batteries. And this pertains to some of the theoretical underpinnings relating to electron flow. Whenever you have a battery, or in this case a cell, we talk about them as cells. One of the main theoretical concepts is that of the standard cell potential, represented as E with a degree sign after it. And the thing about the cell potential, all of this can be thought of as the ability of the cell to do work, or the ability of the cell to transmit electrons one way or the other, okay? And the thing about the standard cell potential is that when you have a redox reaction, which represents the chemical configurations which enable the transmission of electrons from one state to the other state, right, from the positive to the negative terminals of the battery, you have this standard cell potential, which is like, okay, in theory, if you've got cells that are made up of this amount of this and this amount of this, and they've got this, right, and it's all set up just right, then the cell potential is definable, okay? But the thing is that in real life, okay, in actual practice, the cell potential varies, okay? And that is because it may have different temperatures, it may have different air pressure, or there's different things that can affect how fast a given redox reaction will progress and how far it will progress before it achieves equilibrium, okay? So the way to think about this, standard cell potential is what happens when you have standard conditions, where where the temperature is whatever it is, room temperature, and there's it's sea level, right? And it's all these standard conditions apply, and then you can make a general assumption that that's going to be how much oomph, how much energy that cell is going to be able to transmit. But the thing is that the real cell potential, right? So when it says standard cell potential, it means the cell potential in standard conditions. In reality, though, you're going to have a cell whose state is going to be greater or lesser distance from equilibrium, depending on what conditions it is actually in, okay? And so the way to think about this is that the magnitude of the cell potential depends on the disequilibrium between the two sides of the redox reaction based on the conditions that you're actually in that will affect how much electron affinity some of these substances actually have, for that matter, okay? Now, a related concept to this is Gibbs free energy, a standard Gibbs free energy, okay? Again, delta G with another degree sign. The degree, remember, generally means standard, okay? Meaning at standard conditions. So Gibbs free energy is something that comes up in a lot of other contexts, and you'll definitely need to know it for later on in your chemical studies. But it basically corresponds to sort of, if this reaction is allowed to proceed, how much energy is going to be produced from that could be used to do work, okay? And this is particularly relevant if you're talking about like a reaction such as adenosine triphosphate down to adenosine diphosphate, which is the basic source of energy that we use in our cells of our body, okay? So the way to think about the Gibbs free energy, again at standard conditions, is proportional to the negative of the cell potential, okay? So the bigger the cell potential is in the negative, that tells you how much Gibbs free energy is stored up, okay? So think about it like this way, right? So the more cell potential you have, meaning the more potential electrons that are going to be transferred in the redox reaction, the further the redox reaction is going to tend to proceed before it achieves equilibrium, then that tells you there is more stored Gibbs free energy, okay? And the thing is that this Gibbs free energy is not available until it's used, so it becomes you use it as the negative of the potential, and when it's released, then it is used, okay? So just remember it's proportional to the negative of this. Just remember they're the same thing, but the inverse of each other, basically, okay? All right, one more concept. The final and minor curriculum update that you should consider for AP Chemistry relates to some of the language around what calorimetry is used for in the laboratory setting. So calorimetry it comes from the roots calor, meaning heat, and metry, meaning to measure. And as you might imagine, it is a technique for determining the movement of heat in a system, which could be exchanged or could be transferred, could be absorbed, it could be released, depending on what a given chemical system is doing, okay? And the reason that this is worded as saying that it's heat exchange or transmission in a chemical system is that there's a number of ways that heat can be moved around. And for the purposes of calorimetry, all we're really able to notice is heat leaving the system or is heat entering the system. Now, the reason that this is an update is because previous editions of the AP curriculum referred to this as energy instead of heat, or change in energy rather than heat. But really, heat just means change in energy, okay? You can think of it both ways. We're observing this loss of energy through heat, which is means it's an exothermic reaction. It gives off heat. We observe that in a calorimeter, which is basically it's an insulated enclosure, which is supposed to minimize the transmission of heat outside of the system. We're trying to keep the system as isolated as possible. In the solution, there is a reaction that's occurring, or there's some chemical reaction is transpiring, and we have a thermometer which is sticking into this and sticking up out of this, that we can read it, and the part that's sticking up out of this, and we're able to see overall, as the reaction progresses, is the temperature of the solution increasing or decreasing, indicating a release or absorption of heat in this chemical system, okay? And that is then being driven by the chemical reaction that we're witnessing, okay? All right, so just when we're talking about heat, heat means that heat can mean, it can mean cooling down also, right? Because when something gets cold to the touch, that means that it is absorbing the heat, right? When we touch an ice cube that's really cold, heat is still happening, right? Our hand is heating the ice cube. From the ice cube's perspective, we're very hot, right? So in either exchange, there is a little bit of energy that is flowing. Now, remember that in a calorimeter, it's not a perfect system because it is not perfectly isolated. You've got the thermometer that is sticking down into it. This is a little example of Heisenberg's uncertainty principle in action, because by measuring this with a thermometer, the thermometer is itself throwing off your results slightly, okay? So you can never be perfect with these things. Okay.